Hi there! In this video I'm going to show you how you can design and build your own two-stage Wilkinson power divider. I'll explain the theory and show you how you can simulate microstrip structures with a normal SPICE-like simulator. I'll also show you how to make return loss and Smith chart plots with the same simulator. This is really cool as you don't need a specialized tool like Unsoft HFSS or Microwave Studio. Let's get started. So what is a power combiner or divider? Well, we see the symbol here on the left. You have port 1, which is the input port, and you have port 2 and 3, which are output ports. Now, if you put a certain amount of power in here, then you get half the power at port 2 and half the power at port 3. Both these ports will be perfectly in phase. Another criterion is that the isolation between port 2 and 3 should be as high as possible. So if I would put power in here, then no power ideally should come out of here. The characteristic impedance of all these ports should be 50 ohms. It should have an infinite bandwidth. Ideally, it should be bidirectional. So that means if I put power in here and in here, it should come out here at port 1 added together. So let's see how we could do something like this. Well, the most simple way is just tie everything together. But now we have a small problem that the input impedance here at port 1 is 2 times 50 ohm in parallel, which is 25 ohms. So now we have a mismatch. So that's not going to work. So one thing you could do to solve the problem is add resistors. So if you add 3 resistors with a value of Z0 divided by 3, or 50 divided by 3 is 16.6, then you solve all matching problems. It's very broadband because you have no resonating parts in here. So it's very broadband. The only disadvantage is you'll get a lot of loss because these resistors produce heat. What you really want is a transformer. So now if we put in transformers with a ratio of the square root of 2 to 1, you will actually transform the impedance with a factor of 2. And that means that this 50 ohm will appear like 100 ohms here. And this 50 ohms will also appear like 100 ohms here. Then we have basically solved our problem. We haven't solved the isolation problem here because we'll probably get something like minus 60 dB between port 2 and 3, but we're getting much closer to the solution. Those transformer things actually exist. This is a mini circuits power combiner / splitter. And it works from 50 megahertz to 3 gigahertz, which I think is quite amazing for a transformer. So you can just buy these things off the shelf and they will work pretty well. Now there is another way to make transformers, and that's the option I want to investigate during this video. So you can actually use microstrip lines or coaxial lines to transform one impedance to another impedance. You do that by giving them a length of a quarter wave. And here on this schematic you see the symbol. This is basically a transmission line and it has an impedance of 70.70 ohms and a delay of 166.7 picoseconds. That means that this structure will transform 50 ohms into 100 ohms at 1.5 gigahertz. And it's just a piece of PCB trace. Now, before we continue, I first have to explain a little bit about the Smith chart. Now, this is going to be very brief. If you want to know really what a Smith chart works like, Roden Schwartz has a really great 10-minute video on it on YouTube, so you can just look that up. But basically what it is on the x-axis you see the real resistance. So 50 ohms would be here, 50 ohm resistor, and a 100 ohm resistor would be here. And those are the points which are interested to us because we want to transform 50 ohms to 100 ohms so we can parallel those and get 50 ohms again. If you are at a certain point on the Smith chart, let's say 100 ohms, and you add a transmission line to that 100 ohms, the impedance will start spinning around the characteristic impedance of that transmission line. So let's assume I start with 100 ohms and I make a 75 ohm transmission line. I add that to it. Now the impedance will start moving clockwise around that 75 ohms in a circle. It will cross the real axis and it will just keep continuing. So what's interesting about this, if I pick a value somewhere in the middle between 100 and 50 ohms, then it will start rotating from 100 around that point in the middle and end up at 50 at a certain frequency. And this frequency appears to happen at a quarter wavelength. So the idea is we're making a 180 degree rotation here, while the length of the trace is only a quarter of a wavelength, which is 90 degrees. The impedance moves twice as fast around the Smith chart as the length of the transmission line you use, and that's because the signal has to go there twice. It has to go through the transmission line to get to the load and then reflect back, so that's 2 times the length. If you want to get the knowledge of 42 years of experience in electronics and increase your chances of getting your electronics design right the first time, I have a free guide for you. But I'm also working on a paid professional course that goes a lot further. In this course, I'll show you how to take a conceptual schematic and turn it into a working board with a very high chance of getting it right the first time. My designs are almost always first time right, and it's due to a large list of things I learned and rules I've developed. I'm going to show you how to apply all that knowledge as you turn a conceptual schematic into a finished schematic and then turn it into a completed layout. In detailed video presentations, I'll guide you through the whole process. I'll also set up a forum for asking questions, and I plan to have a live video session with the course participants for 1 hour a week for a 4-week time period. All this is meant to completely transform your knowledge on how to successfully develop an electronic product. I have a course information page where you can find more information. Link is in the description. I plan to launch this course in the beginning of 2025. I don't have an exact date yet. I'm not going to rush because I want this course to be the best I can make, and that takes a lot of time. I really hope to see you there and boost your knowledge. In the meantime, check out my free electronic product development checklist. The course is loosely based on that and it's completely free. So let's have a look at a demonstration of this process inside a normal circuit simulator. Now I'm using Symmetrics. I'm not sponsored by them. They have a free student version which you can use to do these experiments, and I think it's a great simulator. So let's have a look. On the left we have a schematic, and on the right we have a primitive Smith chart that was plotted using this simulator. Now let's have a look at the top structure first. We have 50 ohms, then we have a transmission line of 17.7 and a delay of 166.7. We'll get to those numbers later, but 70.7 is exactly in between 50 and 100 ohms. And we simulate that from 0 to 1.5 gigahertz. So at 0 hertz, this transmission line basically does nothing, and we are in the center of the Smith chart, which is 50 ohms. Now at 1.5 gigahertz, we're exactly at 100 ohms. So you can see that this works perfectly, and that you can actually simulate this with a normal circuit simulator. Now this structure here is an ideal lossless transmission line, so you can't make those in real life, but it's perfect for simulation. Now what are all these other structures? I can draw a nice Smith chart. I cannot draw all those nice wiggly lines that I did in Python, so I have to construct something to make it look a little bit like a Smith chart. Now C1, what I've done here, I've picked a short and then a 50 ohm transmission line. So what does that mean? The short is here on the left, the 50 ohm transmission line in the middle. So because of this theory, the impedance starts rotating around that center point, and that makes the outer circle of the Smith chart. So this is a very nice sneaky way of creating an outer edge of a Smith chart. We cannot read impedances here either, but I can make little circles around the impedance, and I guess you've guessed how to do that. You make a 100 ohm impedance, you make a load somewhere close to it, and the impedance will start rotating around it. And that's this blue line. And I can do the same thing around 50 ohm transmission line, 52 ohm impedance, and I get a short circle. So this demonstrates perfectly that you can move the impedance from 50 ohm to 100 ohms using a quarter wave structure. If you simulate this up to 0.75 gigahertz, which is halfway up to 1.5 gigahertz, you see that you're halfway. At 1.5 gigahertz, you've made half the circle, so you're at 100 ohms. And if you continue to 2.7 gigahertz, you're almost around. At 3 gigahertz, you would end up at this spot again. So how can we make these plots? You can use these two formulas. Basically, you can get the coordinates of a Smith chart if you do -1 plus 2 times the real value of S11, which is this voltage here. And you can calculate the y-axis by taking 2 times the imaginary value of S11. So it's really very simple. In Symmetrics, you have something called an F11 window. And you can see here that I've put in this formula here, and that basically then draws this structure. Now I've put in this formula 4 times because I'm creating 4 traces in the simulation, as you can see here. 1, 2, 3, and 4. So now the only challenge we have left is, how do we get these values? So this 17.7 and this 166.7 picoseconds. We want to know the middle between the 50 and the 100 ohm point. So if we could calculate the x-coordinate of 50 and the x-coordinate of 100, take the average value of it, which would be in the middle, then we have to write x-coordinate. Now, if we can convert this x-coordinate back to the impedance on the x-axis, then we know this impedance. So how do we do that? Well, I just showed you that you can calculate the x-coordinate with this formula, -1 plus 2 times the real value of S11. Now, what is the real value of S11? I've drawn it here. It's basically a voltage divider. So you have Z as a load and Z0 as a source impedance. So the real value of S11 is Z divided by Z plus Z0, as I drew here. Now you can fill this in and you get the full formula for calculating the x-coordinate. So now we can do that strategy that I just said. So this is the x-coordinate. We can also write this in the form of Z, and then you get this formula. So now we're also capable of calculating Z if we find x. And now it's simply a matter of filling it in. So 100 ohms appears to be 0.33, 50 ohms appears to be 0. So the middle value is just half of that because one of them is 0, so that's 0.1666. If we fill this in this formula, we get 70.7 ohms, exactly what we would expect. So now the only thing we need to do is calculate the delay time of this transmission line. And that's very simple because all we need to do is find the time of a full wave at 1.5 gigahertz, which is our design frequency, and divide it by 4. So if we do 1 over 1.5 gigahertz, we get 666.677 picoseconds. If we take a quarter of that, then we get 166 picoseconds, which is the exact value that we need. As usual, I wanted to try this. So what I did here is I made a board and I have two 200 ohm resistors. So in parallel, they make 100. The reason I did this is because, yeah, these components have inductance. If I make 2 of them, then the inductance will be less. And you see a lot of vias around here because I also don't want to add extra via inductance. So if you put a lot of them in parallel, you have less inductance. This line here is 70.70 ohms and it converts into a 50 ohm line and then an SMA connector. Later in the video, I'll show you how you can calculate the width of these lines. End result is very nice. As you can see, there is a match pretty close to the 1.5 gigahertz. It's not exact because I use really cheap FR4 board material here. It's not really meant for RF, but the nice thing is I want to show you here that you can do quite a lot with standard board material. You don't need Rogers material to get pretty nice results. And this is the Smith chart of that thing. And we actually see the behavior that we would expect. We start at 100 ohms because at 0 hertz, this whole transformer does nothing. So you just see 100 and you see it's very close to the 100 ohm point. And then it starts moving clockwise. So here we're at 500 megahertz, 1000 megahertz, and at 1.5 gigahertz, we're pretty close to 50 ohm. Now this 1.5 gigahertz point was supposed to be at 50, but this is due to the fact that this board material is not ideal. It's not perfectly characterized. You do not know exactly what kind of epsilon R you're going to get. So furthermore, this connector is not ideal. You will have some discontinuity here. It will not be perfect transfer from the coaxial line to the microstrip due to this connector not being ideal. So you get all kinds of unwanted effects. That's why it's a little bit in a different place. But all in all, it's pretty close. Now the last thing we need before we can actually build a Wilkinson combiner inside the simulator is know how to visualize return loss. Well, this shows the formula for return loss that's generally known, and if we fill in an example like a 200 ohm load, then we get minus 4.4 decibels, and that's shown here. We have a 50 ohm source impedance and a 200 ohm load. We can calculate the return loss by taking 2 times the voltage here minus the voltage here and divide that by the voltage here. If we take the dB value of that, then we have the return loss in decibels. And that's exactly what you see here at the bottom that you can fill in the F11 window of Symmetrics. This is what it looks like in the actual simulator, and you see we get minus 4.43. And this is a little bit more zoomed in so you can see exactly what it looks like. So there's another 2 things we need to look at: port matching and isolation. If you look in here at port 1, we see 100 ohms and 100 ohms. So that's perfect. If you parallel them, you get 50 ohms. Perfect. However, if you look in here, let's see what we get. This 50 ohms turns into 100 ohms here. And we have 50 ohms here. So at this point, we see 50 parallel 100 is 33 ohms. That gets transformed by this transformer. Now this transformer rotates from 50 to 100, so the center point is here. If we start at 33, the circle will become much larger. Actually, we're going this way. And we would end up at 150 ohms. So 33 quarter wave transforms to something like 150. So we would see 150 ohms looking in here. Another thing is that we have 3 dB loss in this direction and 3 dB loss in this direction, so our isolation is only 6 decibels. Now Mr. Wilkinson, who invented this thing, was a very smart cookie, And he found out that if you place a 100 ohm resistor, you solve both of those problems at once. It fixes the matching and it also makes the isolation perfect. You can imagine that a signal traveling here makes 90 degrees of rotation here, 90 degrees here. So it'll be 180 degrees out of phase at this point with respect to that point. And this 100 ohms completely cancels out the signal here. You've got a signal coming in from here in phase. You've got a signal coming in from here out of phase. And by placing 100, the signal perfectly canceled out at the design frequency, in our case 1.5 gigahertz. So very smart solution. Now after all this math and theory, we can finally build a thing in the simulator. This is the actual combiner that I just showed, and I've added some ports so we can measure everything. So these two are to measure the input return loss. This one is to measure the transfer from port 1 to point 2, or called S21. We have a second schematic that is used to measure the matching of port 2 and 3. Now port 2 and 3 are completely identical, so simulating one of them is enough. And we have another schematic to measure the isolation. So we go in here and we see what comes out there. This is the result. We start with the loss basically of the combiner, and we see that's perfectly minus 3 dB at 1.5 gigahertz. The matching, input port matching is perfect. And the isolation is also very good, and the output port matching is also very good. So we see that this works perfectly. Now the main topic of this video is how to design and build a dual stage Wilkinson combiner. So what does that mean? You can make single stage quarter wave transformers. You can also make multiple stage quarter wave transformers, and that will improve the bandwidth. And here you can see what it looks like. Basically another section is added, another section of quarter wave transmission lines and another resistor was added to form this circuit. How do you get these impedances? Well, that's very easy. There are Excel sheets for that where you can calculate it. There's a website called Microwaves 101. They have a ton of information on RF design, and they have this Excel sheet, and you can see the link here. Now it's very simple. You just fill in the amount of sections you want, the center frequency, the bandwidth, system impedance, and it'll just spit out 61 ohms, 82 ohms, and 182 ohms, and 19 8 ohms for the resistors, and it will also show a picture of what this is supposed to look like. So what does this do when we simulate this? Well, we can see that we get multiple dips now in all the characteristics because each transformer covers a part of the frequency range, and they're combined in a very smart way to average it out over the whole band. So this thing was designed from 1 to 2 gigahertz, and you see it's completely flat between 1 to 2 gigahertz, the S21. The S11 has 2 dips. You also see that the other parameters have 2 dips. The isolation has 2 dips, and the S22 even has 3 dips, but you see a very wide area between 1 and 2 gigahertz where this thing operates very well. So now the question is, we have these trace impedances and the length, but how do we determine the layout values? It's very simple. There are a lot of microstrip calculators on the web. If you just Google microstrip calculator, you will find them, but I'm just looking at an example here from EM Talk. You fill in the epsilon R, the dielectric constant, the dielectric height. I'm going to use a 0.8 millimeter board, the frequency 1.5 gigahertz. You just tell what kind of impedance you want, in this 82 ohms, and what electrical length, that's 90. You press synthesize, and this comes out. Very simple, 0.55 millimeters wide, 27.6 millimeters long. Now we can do the same thing for 61 ohm, then you get to 1 millimeter and width and 27 millimeter length. So this is what you get. Here we see the 60 ohm line, here we see the 82 ohm lines, and these half circles have a length of around 27.5 millimeter. These tracks are 50 ohm, and this track is also 50 ohm, so it's very simple. You place the resistors, and this is how you do it. It's really easy. So this is the measurement setup I used to measure it. I'm using a NanoVNA. This is the actual board. I'm using a 20 dB attenuator as a 50 ohm load because I found out that the 50 ohm loads I bought, which were very cheap from AliExpress, only operate correctly until 1 gigahertz. So in the beginning I was wondering why this is not working. But a 20 dB attenuator actually gives you a 40 dB return loss because the signal has to go through there 2 times. It has to go here, 20 dB loss, then reflect back, and another 20 dB loss, so you're at minus 40. So that worked much better because these are 8 gigahertz attenuators. Let's look at the result. This looks very good. Here we see the loss, and it's basically between 3.3 and 3.8 decibels. We see the input matching, which also looks very well. It's at least minus 15 dBs across the 1 to 2 gigahertz range, which is the design range. The S22 is even better, and the isolation is even better than that, with better than 20 dBs over the whole 1 to 2 gigahertz range. It'll be very interesting to compare the ideal simulation and the measurements, and that's what I'm doing here. Mind the scale, the simulation is up to minus 40 and reality is up to minus 30, so you can see that the matching is a little bit less in reality, but all the shapes of the characteristics are very equal. You see a little bit of a slope in the loss that you don't see in the ideal simulation, because in reality you have loss, and you see a little bit of asymmetry in the S11, which you don't have in the ideal simulation. So let's have a closer look at the insertion loss from 1 to 2 gigahertz, and you see that it ranges from minus 3.3 to minus 3.8 decibels. And mind you, this is the cheapest possible FR4 material that you can get, so this is really not bad. Now we can also look at the specifications. So the ideal simulation has an S11 of 25 decibel and we're getting 15, which is not bad at all. And this is all from 1 to 2 gigahertz. The loss is 3 and for the reality is 3.3 to 3.8. The matching of the output ports is 29 decibels in the simulation and we get 19, and the isolation is also 29 in the simulation and we get 20 in real life. Really not bad for very cheap FR4 material working at 1.5 gigahertz. Another thing that's good to realize is that we didn't use any electromagnetic simulators to design this thing. We just converted ideal transmission lines directly into a PCB design and it works absolutely fine. Now this is going to be my longest YouTube video yet, and everybody's always saying that YouTube viewers have the attention span of a fly. So if you made it this far, you've proven you're not part of this group, you have a great attention span, you really want to learn, and you have incredibly good taste. So this is the end of the video. Hope to see you in the next video or any of my other videos. Goodbye.